In this video, let us see about the turbulent flow through pipes. Most flows that we encounter in our daily life are of turbulent flows. Laminar flows are very rare, but most flows are turbulent flows. Let us analyze these turbulent flows in this video. And mainly we will analyze turbulent flow through pipes. So we have seen about laminar flow. So what is laminar flow? It is a smooth flow with a layer by layer, that is called as laminar flow. Random motion of particles, that is called as turbulent flow. Haphazard manner of flowing, that is called as turbulent flow. So in order to define a laminar flow, Reynolds number is used. So if Reynolds number is less than 2000, that is called as laminar flow. If Reynolds number is greater than 4000, that is called as turbulent flow. So this is for pipes. If the flow is through pipes, that is these Reynolds number are valid for laminar and turbulent flow. In case of laminar flow, we use to assume that the flow is steady. So assuming that flow is steady, we have analyzed it. In this case also, the flow is assumed steady, but the velocity fluctuates in this way. So the velocity or some properties. So here the properties are considered to be made up of mean value and a fluctuating component. That means there is a mean value. About this value, there is a fluctuation of the components or properties. So for example, I am saying this is u and this is time t. In this flow, if I consider a particular point, and at this point the velocity is u in this direction. So at time t1, the velocity is this much, and at time t2, suppose this is t2, and velocity is a little bit more, and here the velocity is less. And when the property is plotted with respect to time at a particular point, the velocity fluctuates. So if this is fluctuating, this is a function of time. So as time increases, the velocity is fluctuating. That means velocity is changing. So this velocity is a function of time, and also pressure is also a function of time. Like that, different properties are functions of time. But how can we say that as this is fluctuating and this is a function of time, so how can we say that that is a steady flow? So we can say that it is a steady flow because this fluctuation is random and this has a mean value. If this fluctuation is like this, so this means there is a particular motion and a particular function of time, and that is unsteady flow. But here there is random fluctuation. There is no particular function for it to define. But there is a mean value. There is a mean value for this. So we can consider this as u dash. This is u dash. And so if this is the steady flow one, what if it is an unsteady flow? Unsteady flow means with respect to time, the velocity or the properties changes at a particular point. So this is the unsteady flow, normal unsteady flow. What is turbulent unsteady flow? Here also there is fluctuations of properties. So this is unsteady flow. This fluctuates at mean. This line is the mean velocity at a particular time. That is unsteady flow. So this can be represented as this velocity can be represented as u bar plus u dash. What is u dash? There is fluctuation like this about this mean value. This is the fluctuation. This is called u dash, and this is u dash. So how much it is fluctuating? Above or below the mean value, that is called as u dash. If I need to specify at a time some 2 seconds at this point, so this will be the velocity. That means this u bar plus this u dash. This is u dash. So that is the velocity at that particular time and at that particular point that we consider. So this is u, this is time t. So this is how we represent the properties. If we need to plot pressure, so that is P is equal to P bar plus P dash. This is the mean and this is the fluctuating component. Mainly we find out shear stress and velocity. So these two properties, these two parameters we have analyzed in laminar flow. In this also, these two parameters we will go into analyze. So here, first let us find out what is shear stress. Shear stress. So as the flow is occurring, there will be shear stress. So different scientists gave different formula for shear stress. Bouzinus and Reynolds and Prandtl. So there are different formula for shear stress given by them. So first let us understand this. We will be seeing this boundary layer in separate chapter. So if this is any surface and a flow is approaching here with u infinity, this is the free stream velocity, and due to this obstruction here, there will be boundary layer formed. That means the shear forces are dominant here. That means this is the laminar region. There is smooth flow here, and this is the turbulent region, and this is transition. So if you look in the turbulent region, there is a small layer called laminar sublayer. Here, laminar sublayer, even it is this region is in the turbulent region, but the flow is like mostly laminar. That's why this is called as laminar sublayer. If we need to find shear stress, total shear stress in this turbulent region, that will be tau laminar sublayer plus tau turbulent. So that is the sum of laminar sublayer and turbulent, which gives us total shear stress in the turbulent region. So just remember that. And this Bouzinus gave tau total is equal to mu into du bar by dy plus eta into du bar by dy. So mu is kinematic viscosity. We know that kinematic viscosity, and eta is eddy viscosity. These eddies are the cause of this turbulence. So Bouzinus gave that formula. So this is what? This is tau laminar. This is what? This is tau turbulent. Now, what did Reynolds give? Tau total is equal to mu into du bar by dy minus rho u dash v dash. So he gave this Reynolds. This value u dash v dash bar, this is found as negative from experimental. So from performing experiments, this value is found to be negative. That's why here negative sign is included instead of positive sign. So that is Reynolds. So what is u dash? U dash is, this is u, this is v. So u is u dash plus u bar plus u dash, and v can also be represented as v bar plus v dash. That is also represented in fluctuating and average component. So that is u dash and v dash. And what did Prandtl give? So tau total is equal to mu into du dash by dy. This is common for all, and plus tau turbulent. So he gave tau turbulent as, which is equal to minus rho L square du by dy. Sorry, it is not minus, just rho L square du by dy. He given that u dash is equal to v dash is equal to L into du by dy. So substituting this in this, u dash v dash, that will be L square du by dy whole square. So here it is square. So this is important in our study. Prandtl equation is important in our study. Just remember this. Tau turbulent is equal to rho L square du by dy whole square. So generally this will be neglected, and this is very small laminar sublayer shear stress. So we consider only turbulent one. Then what is this L? L is called Prandtl mixing length. Prandtl mixing length. And this L is equal to K into Y. L is equal to Ky. Then what is K here? K is equal to average roughness height. Average roughness or average roughness height of pipe. So generally this will be 0.4 for pipes. Average roughness height will be 0.4 for pipes. Then what is this Y? Y is the distance from pipe surface. So if this is the surface, Y will be the distance from pipe surface. So this is what shear stress is. So what is shear stress? Tau is equal to rho L square du by dy whole square. This is shear stress. Just remember it. And also I forgot to tell you one thing. There is a measure of turbulence. Measure of turbulence. This turbulence is measured by intensity. Intensity of turbulence. Intensity is equal to 1 by u infinity into under root 1 by 3 into u dash bar square plus v dash bar square plus w dash bar square. This w dash is in a third direction, in 3 dimensions. That will be the third directional velocity, fluctuating velocity. So this u dash, as I said, this u dash is the mean velocity. V dash is the mean velocity in y direction. W dash is the W bar is the mean velocity in z direction. So direct average values are not taken here. U bar is equal to 1 by t integral 0 to t u dt. So this dt is the differential time and t is the total time. So this is the average one. Similarly, for v also, v bar is equal to 1 by t integral 0 to t v dt. Similarly for w. And this RMS value, root mean square value, that is equal to u dash square bar, that is mean value, mean square value. Keeping it root, that will be root mean square value, that is equal to 1 by t integral 0 to t u dash square dt whole root, that will be root mean square value. From this we will be getting these values. So that is the measure of turbulence. And now we have found the shear stress. Another important one parameter we need to find is velocity. So what is velocity? Distribution. So velocity distribution or velocity profile. We will find the equation for velocity profile. So we have found that tau is equal to rho L square du by dy. So we have found this. From this, this is the instantaneous, or what we can say, at that instant the velocity is that much, u is equal to u bar plus u dash. Now this is du by dy whole square. Du by dy whole square is equal to tau by rho L square. So from this we can write du by dy is equal to under root tau by rho L square. So tau by rho goes out and 1 by L remains. We know that L is equal to ky. Substituting this, under root tau by rho into 1 by ky. Now du is equal to under root tau by rho into 1 by ky into dy. So, and also this shear, we know that shear velocity is equal to under root tau by rho. We have seen in the laminar flow that shear velocity, this is called shear velocity. What is shear velocity? Measurement of a shear stress in terms of velocity is called shear velocity. That is also equal to v into under root f by 8. So this under root tau by rho, we can write it as v star into 1 by ky dy. So this is differential one. So integrating it, that will give us u is equal to v star into 1 by k into 1 by y dy. What is 1 by y dy? That is log y plus c. So we have said that k is equal to 0.4 for pipes. So if we substitute k here, 1 by 0.4, that means 1 by 0.4 means 0.25, sorry, 2.5. 2.5. So u is equal to 2.5 v star log y plus c. So this is the velocity distribution. Here log is included, so the distribution is logarithmic. So how will be the distribution? In laminar case, that was parabolic. So that means it was like this. This is the laminar one. In turbulent flow, it is logarithmic. Logarithmic means there is a steep one. So this is the logarithmic distribution velocity. So this is how velocity distribution is in turbulent flow. And another important thing we will find here is roughness. So roughness plays a major role. So pipes can be divided into smooth pipes, transition pipes, and rough pipes. So transition means that is between smooth and smooth and rough. So now this smooth transition and rough pipes are also divided by Nicoradse and Reynolds. So both gave two different notations. So this Nicoradse gave delta dash is equal to 11.6 nu by V star. So here V star into K by nu. So there are two notations given by Nicoradse and Reynolds. So what is this delta dash? We have seen that. So this is laminar and this is transition. This total is turbulent and there is a laminar sublayer. This thickness of laminar sublayer is called delta dash. Now, then what is this K? Average roughness. What is meant by average roughness? If there is a pipe, if there is a surface, that may be surface of pipe, and average roughness. So this is average. Where does the average roughness lie? This will be the average roughness, that is K. If laminar sublayer is greater than K, that is generally considered as smooth one. If the laminar sublayer, this is the thickness of laminar sublayer, and roughness, average roughness of pipe is some here. This is average roughness. Here K is greater than delta dash. That is generally considered as a rough pipe. In precise, Nicoradse gave delta dash is equal to 11.6 nu by V star. This is kinematic viscosity. So by mistakenly I here said as this as kinematic viscosity. That is not kinematic, that is dynamic viscosity. That is called as dynamic viscosity. Now, how do we differentiate this smooth pipe and transition and rough? So if K by delta dash is less than 0.25, that is considered as smooth pipe in case of Nicoradse 1. And this Reynolds gave V star into K by nu. If this is less than 4, that is considered as smooth pipe. And transition 1, if 0.25 less than K by delta dash less than 6, that is called as transition pipe. If 4 less than V star into K by nu less than 100, that is called as transition 1. If K by delta dash is greater than 6, that is called as rough pipe. In this case, V star into K by nu is greater than 100, that is called as rough pipe. So just remember this. This may be useful for 1 mark questions. Now, there is another relation, velocity distribution. Velocity distribution. So what is the velocity distribution that we have seen here? So this one, U is equal to 2.5 V star log Y plus C. This is the velocity distribution we have seen. In terms of friction factor, also velocity distribution can be derived. So, but we don't need derivation. just remember this distribution formula. So U minus V by V star is equal to 5.75 log Y by R plus 3.75. So this is the velocity distribution. So many relations are present in turbulent flow. Actually, turbulent flow up to now, up to this generation, we have analyzed only we have entered only up to introduction of turbulent flow. So there is lot to learn about turbulent flow, but the sciences that we have now are only up to introduction level only. So there is lot to study about a turbulent flow, but we are not going deep into it. So now from this, let us see what is Umax. So where will be the maximum velocity? Maximum velocity will be at center. What means what is center? At y is equal to r. So what is y? From pipe wall surface. So where is the center? At radius r. So now Umax minus V by V star is equal to 5.75 log what is y at y is equal to r plus 3.75. RR gets cancelled and log 1 is 0. That means Umax minus V by V star is equal to 3.75. So remember this relation. So Umax minus V by V star is equal to 3.75. But we can write V star in terms of F, or we can write tau by rho also. So I am writing this in terms of this one. Umax minus V by V into under root F by 8 is equal to 3.75, and Umax Umax by V minus V by V is equal to root F by 8 into 3.75. So sending root F by 8 to right side. So V gets cancelled and Umax by V is equal to 3.75 into root F divided by root 8 plus 1. So this is 1. So Umax by V is equal to, solving 3.75 divided by root 8, we will be getting 1.33 root F plus 1. So remember this. So what do you need to remember? This one and this one and this one. Umax by V is equal to 1.33 root F plus 1. And also tau is equal to rho F V square by 8. So what is this shear stress? Maximum shear stress. This is the maximum shear stress. Tau naught is equal to rho F V square by 8. But in this turbulent one, that is rho L square du by dy whole square. This was the shear stress. But maximum shear stress, this is valid for both laminar and turbulent one. Laminar and turbulent. So this is actually I am writing here tau by rho. This is not tau by rho. This is tau naught by rho. Maximum shear stress divided by density. So tau naught is equal to rho F V square by 8. So how did we get this? Under root of tau naught by rho is equal to V into root F by 8. So this V is average velocity. So from this, tau naught by rho is equal to, squaring both sides, V square into F by 8. tau naught is equal to rho f v square by 8. So this is very important relation. Tau naught is equal to rho f v square by 8. So how to find this f value? So friction factor. What is this friction factor? In laminar flow, it was F is equal to 64 by RE. So then what in turbulent flow? So in turbulent flow, there are two conditions. That may be smooth pipe or that may be a rough pipe. In case of smooth pipe, there is friction factor. The formula for friction factor is F is equal to 0.316 divided by Reynolds number power 1 by 4. So fourth root of Reynolds number here. This is to be used when Reynolds number is less than 10 power 5. So what if it is Reynolds number is greater than 10 power 5 and less than 4 into 10 power 7. 4 into 10 power 7. So in that case, we will be using F is equal to 0.0032 plus 0.221 divided by Reynolds number power 0.232. So this is to be used. Remember all these relations. And in case of rough pipes, mostly this will be used. In case of rough pipes, 1 by root F is equal to 2 log base 10 R by K radius of the pipe by average roughness plus 1.74. So that should be used. This one is also introduced by Nicoradze. So this is all about turbulent flow. This much is enough for GATE and ESE. Mostly in ESE these questions will be asked. In GATE normally this turbulent flow questions may not come. So this is enough for us.